today we're going to be talking about something called piecewise functions, which should probably be a totally new topic for you. So a lot of what we've done so far this year has been a review of things you've seen in Algebra 1, but this I expect is going to be totally new to everybody. So before we jump into the math, I want to ask you a question that does relate to this. What are some moments where all of a sudden everything changes? So like in history or in your life, what is something where all of a sudden, because of this moment, everything's different? Yeah.
Maybe when a car accident happened or someone else.
Okay, so the loss of a loved one, a tragic car accident.
Winning the lottery.
Winning the lottery, everything would be different after that.
Finding out Santa's fake.
Okay, so that is a drastic moment in most people's childhood when they realize that. I actually never got to believe, but for many kids, that's a tragic day.
What?
But some historical events where things really changed a lot because of something that happened. 9/11. So you guys probably don't even remember what things were like really before 9/11, but it was common to, at the airport, go to the gate to greet somebody getting off of a plane, or when somebody was leaving on a trip, you would actually like walk them right to the door of the airplane. And that is definitely something that's not allowed anymore. So a lot of things changed because of that instant right away. What about because we're North Point Christian? What is something that changed everything?
Jesus' crucifixion.
Okay, crucifixion, resurrection. So everything changed because of the resurrection. So there's a lot of things in either personal lives or in national or international or historical events where all of a sudden something changes, and it can be an extreme change. And that's what we're going to actually see in piecewise functions, is that all of a sudden we're going to have a big change. A piecewise function not working. Let's try this again. Okay. A piecewise function is defined in two different sections of the domain. So what a piecewise function will look like is like this example where we've got our function notation f of x, and then it says it equals, but it equals different things at different times. So if x is smaller than 1, we have one thing going on. But once x becomes bigger than 1, we've got something else going on. Okay? There's a special kind of a piecewise function that looks like stair steps, and so we're just defining that here, but we'll take a look at those in a little bit. So first thing we want to know is how do we evaluate it? So we've talked about evaluating functions this year, and so what we want to know is how do we evaluate it? There's two different functions here, but we don't always evaluate both because only one is true at a given time. So what we have to do is decide which piece is true and then evaluate just that piece. So when x is 0, we look at our criteria over here and say which one of those is true if x is 0. The first one or the second one? The first one, because 0 is smaller than 2. Okay? So we look at the value we're working with, which is 0, and decide which piece that's true for. 0 is less than 2, so that means we're going to be working with the first piece for this problem. And then we're going to plug into just the first piece. So plug in a 0 for x, and what do we get?
0.
So f of 0 is 2. If I plug a 0 in for x in that first piece, I get 0 plus 2, which is 2. For the next one, if x equals 2, which one of those two inequality statements is true?
Second one.
The second one. How can we tell?
Because it's equal to.
Because it has the equal to. Okay, so they both have the 2, but what we have to look at is which one is true when x is equal to 2, and that's the one with the equal to bar. So here we're working with the second one. So then we're going to plug 2 in there. So if I plug in 2 in for x in that second piece, I would have 2 times 2 plus 1, which is 5.
Wait, what?
So I plug 2 into the second piece, since that's the one that's true when x
Oh,
equals
okay.
2. So 2 times 2 plus 1 is 5. For the last one, when x equals 4, which of those two statements is true?
Second one.
The second one, because 4 is bigger than 2. So we're going to plug into that second one again and say f of 4 equals, and plug in a 4. 2 times 4 plus 1 is 9. Okay. So to evaluate a piecewise function, you have to determine which piece you want to plug it into, not both. Determine which piece you want to plug it into based on the inequalities, and then plug it into just that piece. Questions? Okay, so for this one, when x is equal to 0, which piece am I going to plug into? The first one, because 0 is smaller than 3. So I look at those inequalities and determine which one makes it true. 0 is smaller than 3, so the first one is true. So f of 0 equals what? 2. Because if I plug a 0 in there, 3 times 0 plus 2 is 2. Which one is true when x equals 3?
First one.
The first one, because it has the equal to bar. So 3 equals 3 happens in the first statement. And what do I get when I plug 3 into the first statement? 11. 3 times 3 plus 2 is 11. And the last one, if x is 6, which piece is true? The second one, because 6 is bigger than 3. So if I plug a 6 in there, what do I get? 5.
You have to do like the inequalities part first, and then
Yep.
then
So-
after that, it really doesn't matter.
Right. So we don't actually use the inequality to do the evaluation. We use the inequality to determine which piece to evaluate. Yep. So that's your first step, is looking at the inequality to determine which piece to evaluate, and then you just look at what's before that semicolon. All right. So I have a question then for you to try out. So if f of x is equal to Okay, so given that piecewise function, I want you to take a few minutes and go ahead and evaluate those 5 different values. Okay, so which piece is true if x equals 2? The top or the bottom?
Bottom.
The bottom. So that's one that has the equal to bar for the 2. So f of 2, we're going to plug 2 into just the bottom piece, and I get 2 minus 4 is negative 2. For negative 3, which piece is true?
The top one.
The top one. Negative 3 is smaller than 2, so we're working with just the top piece. And what do I get if I plug in a negative 3?
11.
Positive 11. Negative 3 times negative 3, 9 plus 2 is 11. Just plugging into the top piece there. Which piece do I plug into for 0?
Top.
The top one, because 0 is smaller than 2. And what do I get?
2.
2. And which piece do I plug in for a negative 2? The top, because negative 2 is smaller than 2. What do I get?
8.
And which piece do I plug in for a 1? The top. Because 1 is smaller than 2. So you get negative 1. Okay? So you determine which piece to plug it in based on the inequality, and then you plug it into just the stuff that comes before the semicolon. Or sometimes it'll say like comma and the word if, but you just plug it into the front part.
So even though negative 2 is, or even though like 11, like it doesn't make sense in the x is less than 2 or whatever.
We don't look at the answer in terms of the inequality, just the x value. So whatever's in the parentheses is our x value. So we determine negative 3 fits in where? Negative 3 is smaller than 2. And then we plug it in. It doesn't matter what you get out. It doesn't matter if the outcome fits the inequality or not. Because the outcome is a y value. So that doesn't matter. It only matters if the input, the x, fits the inequality, because what you get out is actually a y. Okay. Okay, so then graphing these. To graph them, what I do is I start by making a big vertical line at this breaking point. That's the instant that everything changes. So what I'm going to do is figure out where is that breaking point, and in this problem, it's at 1. So at x is 1, I'm going to make myself a vertical line. It's not actually part of the graph, it's just going to help me make my graph. Okay, it's not technically part of the graph, but it's a helper. Then what we're going to do is graph the 2 individual lines. So I'm going to graph the first equation. It's in slope-intercept form. So I have an intercept of 1.5, 3/2, and a slope of up 1 over 2. And get myself some extra points because I'm not good at drawing straight lines. And I'm going to graph in that line. Pencils, by the way, are going to be really good for this on your homework.
Yay.
Then I'm going to graph the second line. Slope-intercept form again. So I have an intercept of 3 and a slope of negative 1. So I'm going to draw those in. Now these are not both always true. If they were, we would have some function problems here, right? Because our vertical line test would fail us. So they're not both always true, so then we need to determine which one is true when, and we're going to erase half of each of these lines. So if x is smaller than 1, that means to the left of 1, I should really only have the blue piece. So I'm going to erase the purple that's over on that side. I don't really need that. And if x is bigger than 1, I should really only have the purple piece. So I'm going to erase the blue on that side. In the end, it should pass the vertical line test, so you should only have one piece on each side, and there should be half of each of the pieces. Okay, you wouldn't want to erase one complete thing. Okay, and then we can put arrows on the ends, and that's our answer. Technically, the red line is not really part of the answer, it just kind of helps us, but you don't have to erase it. You do have to erase the portions that shouldn't really be there, the portions that make us fail our vertical line test.
Where did the vertical line come from?
From the inequality. So wherever that breaks apart our x's, whatever x is greater than and less than, that's where we're going to put our vertical line. Okay. Just kind of 3 steps. So we put that vertical line in, well maybe 4. We put that vertical line in, we graph each individual line, and then we erase half of each of those lines. Okay? Let's do another one together. So where is this one going to break apart?
3.
At 3. Okay, so x is 3. I'm going to make my vertical line. Then I'm gonna graph my first line. Slope intercept form, I have an intercept of 2 and a slope of up 3 over 1. Okay, so I really need to be able to get it at least to that red line. So I'm just gonna have to kind of keep on heading up here. Maybe scaling by something else would have been appropriate in this problem, but. Then I'm going to graph the second one. Intercept of -1. Slope of up 1 over 1. But they are not both always true. So then we have to determine what we're erasing here. Where is the blue one true? Less than 3. So the blue one should be true on the left of that line. Less than goes to the left, so the little bit that I had on the right there I actually want to erase. The purple one says it is true if x is greater than 3. So that means to the right of 3, so I want to erase everything that's over on the left of that one. And so I'm left with the blue piece on the left and the purple one on the right. Now the last one, they came together perfectly. They actually met at the same point, and this one they don't. And that's okay. Sometimes they'll meet up, sometimes they won't. If they don't meet up, we have one additional thing we need to consider, and that's what to do at those end points. So put arrows on the ends that go on forever, but at the end points on that breaking line, we need to use open and closed circles like we did when we graphed on a number line. So for the equal to piece, which is the blue one, I need a closed circle. And for the not equal to piece, which was the purple one, I need an open circle. And that's what makes sure that we don't fail our vertical line test. If they were both closed circles, we would be failing our vertical line test there. So if they meet up perfectly, you don't have to worry about that. But if they separate, then at their endpoints, the equal to bar piece gets a closed circle, the not equal to bar piece gets an open circle.
Why don't we just do dashed and solid lines like
Dashed and solid is if we're graphing a complete inequality. Where we're actually graphing has the equals with the f of x, so it's an equation. It's just the inequality is breaking apart the two pieces. That's a good question. A lot of students get confused on that since yesterday we were doing dotteds and solids. Questions?
So why didn't we do closed and open circles right the first?
Because they met up perfectly. So there wasn't really an endpoint because the two pieces came together. So if we gave one a closed circle and one an open circle, they're going to overlap each other anyway. But if they're in separate pieces, then we need to worry about what the endpoints are. All right, so your turn to try one.
Do we have to do the circles?
If they don't meet up. So if they meet up perfectly, then you don't have to. But if they don't meet up, then
On that one.
Hmm?
If they don't move up on that one.
yeah, yep. So if the two pieces are ending in separate points. Okay, so go ahead and try graphing this one. Graph your vertical line where the break happens first. Graph the two individual slope-intercept equations. And then erase half of each of them. When they don't meet up, put closed and open circles. Okay, so the first thing I'm going to do is put in my separating line at x is 2. So at x is 2, this graph is going to break apart and do different things. Then I'm going to graph my two individual lines using slope-intercept. So the first one has an intercept of 2 and a slope of down 3 over 1. I'm going to graph that out. Then I'm going to graph out my second line. It has an intercept of -4 and a slope of up 1/1. Then I'm gonna have to erase half of each of these lines. So I look at the inequalities and say the blue one should exist only for x is smaller than 2. So the blue one should exist only on the left of that breaking line. So this little tail over on the right, I don't want. Then the second one, the purple one, should exist only if x is bigger than 2. So I don't want the part over on the left of that one. Then I need to consider what's happening at those endpoints since they didn't meet up perfectly. So the blue one, the inequality does not have an equal to bar, so it needs an open circle. The purple one had an inequality with an equal to bar, so it gets a closed circle. And our final answer should look like those two little rays going out in different directions.
Do you erase what's wrong or what's right?
Erase what's wrong. Yeah. So I kept the blue on the left for the less than and kept the purple on the right for the greater than. So erase the part that does not meet the inequality. Questions? Okay, we're about halfway through our lesson, which is exactly where I wanted to be, which means that you don't have any homework due Monday.
Yay.